Okay, welcome back everyone. In this video, we're going to continue our discussion of electromagnetism. And last time we looked at Faraday's law and also Lenz's law of electromagnetic induction to try to determine how a changing magnetic field could induce a current. But now we're going to look at a situation that is a little bit strange. So here's our solenoid again. And in this picture, part A, you can see that the solenoid has a magnetic field that's going kind of into the page. You can see the blue arrow right here for the magnetic field. And imagine that you have a current in a wire surrounding the solenoid that has a value of I, but it's also changing at a rate di dt. Now, because this current is changing, there's going to be a change in the flux. And here's what is kind of interesting, is that this change in flux is going to induce an induced current, I prime, in a random wire which we just place around the solenoid. But here's the surprising thing, is that there's not actually a magnetic field outside of the solenoid. Okay, in other words, if I have a segment of wire right here, a segment of this wire loop, there's not actually a magnetic field there that causes a force on the moving charges. So how then do we explain that we have current in that wire loop? Well, so basically what happens is that there's going to be a current from a changing electric field. And so another alternative formulation of Faraday's law is actually that an induced voltage is equal to the circular or the path integral of E dot ds times a charge Q. So one way to think about this is that work is equal to Q times V. So the work per unit charge is also known as the voltage. So remember that work is equal to QV and voltage is negative integral of E dr, or ds in this case. And so really what happens here is that we get the loop integral of E dot ds going around a changing flux is equal to the EMF. Okay? So this is another formulation of Faraday's law. And basically what this says is that as a charge goes around that wire loop, work is done on that charge. And the amount of work that's done is equal to the value of the charge times the EMF. And so this is just another way to look at Faraday's law of electromagnetic flux. So here's a quick example using this. So we have a circular magnetic field, and it's got a radius of 1 meter, and it's decreasing at a rate of 4 milliteslas per second. So we've seen this setup before. We want to find the magnitude of the induced electric field 0.5 meters from the center of the magnetic field during this time, and then we also want to look at 1 meter and 1.2 meters. So what we want to set up here is our loop integral, that the integral of E dot ds at a particular place is going to be equal to negative d flux dt. Okay, now this EDS is going to be essentially 2 pi r times the value of the electric field, and then this is going to be negative a dB dt. Now, it's important to point out that this A right here is equal to pi r squared. And this is not necessarily the same as this r right here. Because, for example, if we have a loop that's going around everything, we have an r that's much greater, but the flux is only changing within an area of big R. So in other words, little r and big R could be different. But in any case, E is equal to negative pi big R squared dB dt over 2 pi little r. So those cancel, and we have essentially negative r squared dB dt over 2r. And then we can go ahead and plug in, and we're not going to do that right now, but you can just plug in that r is 1 and dB dt, big R is 1 to begin with, okay? And little r is going to vary from 0.5 to 1 to 1.2 depending on the situation, and dB dt is just going to be negative 4 millitesla per second. So we're going to get a value of the electric field that's going to be sort of in a positive direction or counterclockwise. And so let's see kind of how that comes from Lenz's law. Okay, so the initial field is coming out of the page. So we've done this before, out of the page and into the page. The final field is going to be less, but also out of the page, which means that the change is into the page, and so therefore the induced magnetic field will also be coming out of the page. And because we've done this before, your thumb is coming out of the page, we're going to have a counterclockwise current flow. And notice that because current is the direction of positive charge, that makes sense that the electric field is going to be tangent to that circle in the same direction as the current. So if the current is going this way, at any particular point, the field will be tangent, because that's the direction of the force on positive charges. Okay, so that's just a very quick look at another way to calculate EMF. So in the next video, we're going to start looking at inductors and the role that they play in circuits.